Hello everyone. It's a great pleasure to have Jens Chluba here today. Thanks a lot for accepting our invitation. Jens is now Professor of Cosmology at JBCA at the University of Manchester in the UK, while he did his PhD and first postdoc at the Max Planck Institute for Astrophysics in Germany. He then joined the Canadian Institute for Theoretical Astrophysics as a postdoc and the Johns Hopkins University to finally become a Royal Society URF at Cambridge University before moving permanently to Manchester. Jens is a leading expert on cosmological recombination physics, CMB physics, and spectral distortion caused by early energy release, and the Sunyaev-Zeldovich effect. Today, he will present CMB spectral distortions and how they may help with the Hubble tension. Jens, please, you can start when you're ready.
Thanks a lot, Nora. So welcome, everybody. I'm very happy to be giving my first seminar this year here as part of the CosmoVerse series. And yeah, indeed, I want to try to tell you a little bit about why spectral distortions are really exciting and why I think many people should be really excited about spectral distortion science that you can do. But then, of course, also link it back to the Hubble tension and why maybe even spectral distortions will be one of the ways to learn about this. So yeah, obviously, when we think about the CMB, most people just immediately think about the beautiful map that we have of the sky, of the temperature anisotropies. The temperature anisotropies, there's no need to explain, have really taught us a lot about cosmology and the universe that we live in and the properties of the universe. But it is really not the topic of this talk at all. For me, I'm looking at the average sky signal. This is really important because it's something that everybody always misses. It's literally about the energy distribution of the microwave background rather than the anisotropies in the temperature. So we're looking at the energy distribution, the spectrum of the microwave background, and the spectrum has been shown to be extremely close to that of a black body by the COBE FIRAS measurements. In some 30 years ago now, and we are with spectral distortion science basically focusing on departures from this perfect black body shape. So there is these typical distortion shapes that people talk about, the mu-type distortion and the y-type distortion. The limits from COBE FIRAS, they give you extremely tight upper bounds on these distortion parameters, as you can see at the level of 10 to minus 5. In terms of energy, 10 to the minus 6 times 10 to the minus 5 or so. These distortions, they are classical distortion shapes that have been, known and described many, many years ago by the seminal papers by Rashid Sunyaev and Zeldovich. So the y-type distortion is one of the distortions that occurs in some sense in the late time universe. For me, late time universe means at redshifts below 50,000. So obviously, this is well before any structures and things like that form. So most people are like, yeah, this guy is crazy, low redshift universe. But 50,000 is a critical number because it tells you when the universe becomes cold enough and dilute enough to not have strong compensation effects anymore. So you, as you can see here in the, let me make sure, in the left figure, where the microwave background basically just gets upscattered by the hot gas in the universe. This is also known in connection with the Sunyaev-Zeldovich effect, where you have the hot gas in clusters of galaxies, of course. This is an exaggerated case, just to illustrate. It's a small increment in the energy, and you're shifting the black body shape, basically. While conserving number of photons. And then in the right, you see the mu-type distortion, specifically the solid black thick line labeled D, which is essentially the same process, comptonization of hot electrons. But in this case, you have the comptonization is so efficient that you can really move the photons across the full spectrum of the microwave background. And this is the two regimes: the optically thick or very, very strong comptonization regime and the much less efficient comptonization regime. And in more modern version, you're actually plotting directly the distortion shape. So you're looking at the difference with respect to the black body, because of course the distortions are very small. So you want to take out the leading order term, namely the black body part. And this gives you this kind of spectral shapes. So 3 curves here. One is the full thermalization curve, which is just meaning that when you have a black body of a slightly lower temperature, you would have to add the number of photons in this way, with this red curve, to shift it to a higher temperature black body. Or of course, you could remove it. That's the CMB anisotropies for you. And then you have the blue curve, which is the mu distortion type. And as you can see, it is slightly different from the black curve, which is the Y distortion. And that means that you can, in principle, observationally distinguish these kind of signals. And the mu distortion is something that comes from the early redshift universe, from the high redshift universe, which is meaning that you're really probing primordial physics. Okay, so let's put this into context. The spectral distortions. This is just a timeline of the universe, and you have seen this many times. Spectral CMB anisotropies, so the temperature patterns, we use them to learn about inflation, the early phases of the universe, by looking at the statistics of these fluctuations. Then, of course, there's lots of things happening at late times as well. But the CMB anisotropy science, I don't want to go and cover this much more. Spectral distortions, they probe energetic processes or out of equilibrium processes, basically over a vast range of cosmic history, starting from something like 2 months after the Big Bang, a redshift of a couple of million, until today. So by measuring spectral distortions, you can in principle open a new window to this, early universe physics, where you're looking beyond the last scattering surface. So even earlier than the CMB anisotropies can directly probe, and specifically the mu-type distortion. So this means that you can, with spectral distortions, you can learn about the thermal history, about energy release processes, and about the early universe, opening an unexplored window, which we have no access to at the moment. Putting the distortions again into the context. So I told you the 50,000 is the critical number below which you have the Y-type distortion. In this figure, of course, that's a vast range of time that is really covered in this way in the late time distortion. But then the mu-type distortion is the distortion that really probes the primordial physics. And you can estimate these distortions. This is well known from the seminal papers by just looking at what amount of energy was really injected, and that immediately gives you estimates for the corresponding parameters. We now understand that this transition between mu and y is not just an abrupt, mu distortion versus y, but there's actually an intermediate distortion where you're basically transitioning from one type to the other, and there's nonlinear new physics information, new quantization information, which basically gives you a time-dependent information that you can use to distinguish different distortion shapes. So this adds a whole nother direction to the distortion science, and is really, really interesting in terms of exploring the universe, the early universe physics. And there's also the hydrogen and helium recombination lines, which I will get back to at the end, also when I'm talking about the Hubble tension and how this is potentially all connected. Yeah, just one word. We can calculate these distortion shapes now for many, many scenarios very, very simply with the code CosmoTherm. It allows you to inject energy from decaying particles. Photon injection cases can be treated. You can even do anisotropic spectral distortions. If I have time, I will maybe flash a few slides at the end about this as well, which I'm pretty excited about. But in general, just I want to say the physics of calculating the distortion is really well understood. It's all similar to CMB anisotropic physics, where you're basically knowing how to propagate through the universe the photon field and the evolution of this. And then you can probe the physics of what creates the distortions. So you're having a potential to really map back to the physics of the distortion sources, which is really exciting about this. Okay, so why is spectral distortion science interesting? Well, because you can really probe a wide range of physical processes. This is just one very busy figure that we put in one of the white papers that we had on the topic, where we basically, you can think about the y-axis as sensitivity or signal strength, and the x-axis is, of course, the different epochs again. Yeah, there's two types of signals here. One is the yellow types, which are standard distortion sources, which are expected lambda CDM distortions. So this is exciting because you actually have targets that you can tailor your experiment for, and you can learn about various processes, for example, the structure formation and ionization process at late time, and then also probe the small scale acoustic modes and things like the recombination era. Then there's, of course, the new physics examples, which are the discovery space that you can look at. And just if you look at the list of processes that I have, squeezed into this figure, there's things that you probably can get excited about because, things like primordial black holes, dark photons, axions, cosmic strings, primordial magnetic fields. I mean, these are all processes and all topics that people are talking about, and spectral distortions have a handle on this. So you can learn about these processes and really, study early universe phenomena with spectral distortions. And here is just a summary, one summary slide of all the expected lambda CDM distortions. The largest distortion comes from the late universe, which is the average Y distortion at the level of 2 × 10⁻⁶. So an energy release of order 10⁻⁶, as I already explained. This distortion is a booming signal in terms of like sensitivities that future spectrometers here as a guideline, some level of Pixie sensitivity, which is one of the spectrometers that people are talking about. This is a booming signal with respect to these kind of sensitivities that we can in principle reach nowadays. There is, of course, then the relativistic correction to this signal, which allows you to basically break the degeneracy between the pressure, the total pressure of the universe, but also the temperature of the universe. So you can really measure the learn about structure formation and the energy release processes during the structure formation process. And then there's the very interesting signal coming from the acoustic modes at small scales. This is something I'm going to try to elaborate on a little bit, because it's probably one of the main reasons why spectral distortions are seen as one really important and crucial early universe probe that we should be really thinking about how to open the window to this. And then there's the recombination lines and also a cooling distortion coming from the fact that the baryons and photons have a slightly different adiabatic index and cool differently when the universe expands. So even in the absence of any extra energy release or any non-standard physics, these distortions should be there, and they are coming from various physical processes. So the other reason why things are exciting is because, we have not made any real significant progress since COBE FIRAS on this topic in terms of the experimental frontier, but has been a huge amount of activity trying to discuss which kind of experiments could be, which concepts could be improving over the FIRAS limits. And Pixie, I mentioned it already, is one of the space mission concepts that has been, now discussed for probably 15 years almost. And it could improve the sensitivity of FIRAS by a factor of 1,000 or 10,000. And different versions of Pixie, basically, copies of Pixie or different, ways of splitting the frequency bands, that's going to be really opening the window to all of these kind of interesting signals. And one of the other aspects is there is also activity already starting from the ground and balloon, which is not fiction anymore. This is really happening now. TMS, for example, is expected to probably measure in the next couple, maybe even by the end of this year in the 10 to 20 gigahertz regime from the ground in Tenerife. José Alberto Puito Martin is the main PI of this. And that will be something that will be teaching us probably about the arcade excess and also look at the Y distortion. And then very exciting, BIZU is now officially, since last May, has moved to the phase A in CNES, which really, is hopefully going to create a lot of activity, and within 5 years or so from now, hopefully will be really leading to the first measurements from a balloon experiment, which will improve the limits on Y, or even hopefully detect the Y distortion. Over FIRAS will be a factor of 20 to 30 improvements. So this is all exciting, and then of course builds up towards potentially a space mission. We are thinking about reproposing fossil, led by the French community, Nabila Aghanim and Bruno Maffei. We are thinking about reproposing this for the M8 call now. So, and just to close up the introductory excitement part of the talk, there is clearly an indication that the community is realizing how important spectral distortions are, because this Voyage 2050 call has explicitly mentioned spectral distortions as one of the potential probes of new physics in the early universe, together also with the gravitational wave proposals or white papers that were put in. So this is really exciting, and it means that one has to start thinking about things now, moving things forward. aspects like TMS, Cosmo, and BZoo are, of course, really crucial. And I'm really excited, as I said, that this is happening now and starting to change the field from this 30-year dormancy to something that is really, we're hoping to have some real data actually to play with. And of course, I mentioned already fossil as an M8 call. That might be a really interesting opportunity to actually do something that is on a more intermediate timescale, and also a more intermediate step in terms of not overcoming immediately a factor of 10,000 in parameter space, right? Because this is a transformational measurement. If you do a factor of 100 improvement over a previous experiment, that is really an exciting opportunity. Okay, so I just want to say a few words about the Early Universe probe, which I think is really one of the key drivers for spectral distortion science as an interesting topic. And we all, of course, heard about the detections of the gravitational waves a couple of years ago. And well, a couple of years is maybe already a little bit too light. But we have opened this window to gravitational wave astronomy, which is extremely exciting. But this was, of course, raising the question: is there some connection with primordial black holes? Potentially, right? Of course, we know now that the various parameter spaces have been excluded. This is here the fraction of primordial black holes as in relative to the amount of dark matter from a recent paper by Carr and company. And it just shows, of course, that simple solutions like, okay, there's like 30 solar mass primordial black holes. These kind of things don't work anymore. But you can, in principle, imagine distributed, non-monochromatic or mono mass, solutions to this, or even just a significant fraction of dark matter is made of primordial black holes. Anyway, the story is extremely interesting, and of course, we all heard about the nanograph, this discovery or detection of the stochastic gravitational wave background, and one of the possible explanations is, of course, that this is sourced by some primordial physics, some primordial, potentially even primordially induced physics, and primordial black holes could play a role in this sense. And I was really happy when the papers came out from the EPTA collaboration, where they actually considered the constraints that FIRAS already puts on models in terms of power spectrum constraints. So this is here in the left figure, you can see FIRAS already excludes this parameter space. And I just want to say, this is like 30-year-old data, right? So this is really interesting in terms of like the physics that is being probed and discussed currently, right? So why is the spectral distortions interesting? Well, I mentioned it already. FIRAS puts constraints on the amplitude of scalar fluctuations at small scales. So this is a very, very wide range plot of the power spectrum constraints that we do have. At larger scales, we of course know the amplitude of the fluctuations to extremely high precision with measurements from Planck and CMB experiments, of course, and then also large-scale probes, Lyman alpha forest, all this. But at around 1 inverse megaparsec or so, we're of course running out of steam, because this is going into the territory of very, very small scales. Then you have all this, future activities and also existing activities that with pulsar timing and interferometric experiments will be, probing the very, very small scale amplitude. And in the middle, you have the spectral distortion constraints. So FIRAS already rules out basically the possibility of forming supermassive black holes, which we see in every galaxy by just primordial collapse of horizon scale perturbations when they enter when they become dynamical, right? So this is, the amplitude cannot be large enough to really make this happen. And of course, there's some discussion, some discussions about whether you can fix this avoid this constraint by using primordial universality to create these, but I believe that it's now clear that supermassive black hole horizon scale collapse is going to be a very difficult story to sell. But at smaller scales, first of all, the scalar amplitude is not constrained as much, and there's also the intermediate mass black holes scales that could be part of the story of what spectral is relating to the formation of black holes that we see in galaxies, right? So Let me just say a few words. Of course, this this already shows you, and especially when you look at the lines that we have here forecasted for Pixie-type experiments, assuming that you will detect a mu distortion of order 10 to minus 8, this already shows you that you are really with spectral distortions filling in a gap that is extremely important. And of course, when you think about these scenarios, let's say you really want to have large amplitude fluctuations here. Getting from here to there is not easy. You can't just do a step function, increase. So you will always have some signals that in principle, lead to this rise of scalar perturbations. So spectral distortions will play a really crucial role in understanding the physics going on at small scales. And this is why I'm writing here, that this could be really an important way to shed light on the formation process. But let me just say 2-3 words about how this actually works. It's very simple. Now we're really interested in the fluctuations, but we're basically looking at the smallest scales. And from measurements with CMB anisotropies, we know that the power spectrum drops like a rock at small scales, exponentially cuts off because of silk damping. If you were able to undo that silk damping, which you can of course theoretically do when you're just switching off and on the corresponding evolution terms in the photon-Boltzmann equation, then you would see that the amplitude of the fluctuations is basically scale invariant by at least in slow roll inflation models. And the reduction of the amplitude at small scales, that is the cause of energy release, simply because you have black bodies of different temperatures mix. So how can you think about that? Very simply, if you take two black bodies in a small volume element of the universe at small scales, one being a little bit higher temperature, one being a little lower temperature, then of course the temperatures, the black bodies of these two temperatures here, the hotter one is the red curve, the colder one, the blue curve, and the average temperature black body would be the dashed line, right? If you now take this box and you shake it or mix it up, for example, through the Thomson scattering, but without changing the energy distribution of the photons or without adding extra photons to the field, you would just be getting a uniform distribution, this purple, universe patch, and the purple distribution of photons. As you can see, this is not a black body of the average temperature because you have actually just mixed photons, but you haven't added the number of photons, you haven't increased the number of photons, nor have you added extra energy to the process. So you basically have a Y-type distortion to leading order, and that then starts the quantization process, and you get a mu-type distortion on average from this mixing process. That's how you learn about the small-scale power spectrum, by basically the physics of the dissipation of these small-scale acoustic modes. Okay, and I want to link this back now really to the primordial black hole and supermassive black hole story in terms of the pulsar timing measurements. I was last year at the EPTA meeting in Sesto, and there were many of the discussions were of course about what is really causing the stochastic background, as we understand evidently, and the vanilla explanation is of course this is just supermassive black hole mergers, and I heard several times in the audience, oh, there's no problem, it's all solved. But we have a problem. We don't really know these supermassive black holes, how did they really form? Because when you just do adding limited accretion or even super adding and accretion, it seems like we don't have enough time to really form them, or at least in the standard models, you need to still put some ingredients that are not understood or not completely clear. So there might be also the necessity to just add some intermediate black holes, intermediate mass black holes that could be of primordial origin, for example. There's of course other alternative explanations like cosmic strings and phase transitions, and all these aspects are also being discussed. But the important thing is we still don't understand where these supermassive black holes would come from, and there might be a link to primordial physics. And if you want to really understand the origin of this gravitational wave signal, this stochastic background, we will probably ultimately need to combine various probes. And as I just told you, with spectral distortions, we learn about the small-scale power spectrum. If really we believe there's primordial origin of primordial black holes or something, we should see probably a distortion. Unless this is extremely small mass, low mass primordial black holes, it is very unlikely that we will avoid the enhancement needed from the CMB scales to the small scales, that we will avoid a signal in the spectral distortion regime. So this is an interesting link that one really needs to think about. And there's also the second aspect, because the stochastic background is, of course, scalar-induced gravitational waves would be the key link here. And this is just a template of like how the gravitational wave emission would look from a delta function in the K-space of scalar perturbations. And with this, you can put a limit now on the gravitational wave amplitude, which is allowed from scalar perturbations by just combining the FIRAS constraints and everything to put this into the figure. So this is a figure that Bryce Sear put together that shows how the blue region is actually ruled out by combining spectral distortion constraints from FIRAS and all the other existing scalar amplitude limits. How that cuts into the parameter space. And there's one really important message to take away here. First of all, the direct dissipation of gravitational waves is actually, you can learn about these as well. The limits are not very competitive from FIRAS, but with PIXI and Voyage 2050, you might be able to push into regimes where you actually probe some level of new parameter space in regimes that are not covered otherwise. So this is important because it will be allowing you to directly look at the gravitational wave-induced spectral distortion. But the more important aspect is, of course, if these gravitational waves are coming from scalar perturbations, then you would be, oops, I'm going in the wrong direction. You would be having this indirect scalar-induced limit on the larger scales. And FIRAS rules out the blue curves, the blue region. But you see here, LightBird is going to probe in this regime at very large scales. It could be that LightBird will, if there is indeed some scalar-induced primordial, scalar-induced gravitational waves, that LightBird could see this signal, but it wouldn't be able to probably say if it is really scalar-induced or not. With PIXI, this is the green curve, you could rule out that contribution to be significant at LightBird scale. So this is a synergy of CMB anisotropy and B-mode searches with spectral distortions. Okay, so I'm now getting to basically the Hubble tension, but it's just one intermediate step that I want to say there, namely the arcade excess. This is, in some sense, a spectral distortion that we have not explained yet, potentially a spectral distortion that we have not explained yet. And it's interesting because it could be directly related, of course, to gravitational wave, to the gravitational wave signals as well. Because if you have black holes or structure formation happening much earlier, and you have the signals creating the stochastic background, well, then structure formation might set on much earlier and lead to radio emission as well. So what is the arcade excess for those that haven't heard about this very lately? This is a synchrotron-like excess that has been measured by the Arcade 2, or it was put into context by the Arcade 2 measurement in 2011. It has more recently been confirmed at lower frequencies by the LWA, Dowell and Taylor is the reference to look up for. And it looks like this signal is something that we cannot explain with, for example, stacking all radio sources that we have, making a population synthesis, or explaining the synchrotron emission from the galaxy. It seems like this is all falling short. So there is a quasi-isotropic radio excess signal that is still unexplained. And for recent discussion, I point towards these papers from Jackson Gall in 2018 and 2023. I was actually at this workshop in 2023, and I was going there with the 100% belief that I would be hearing, oh, this is easy to explain. And it was when I at the workshop, it became clear that even the different experts from different communities, everybody agrees that this is a signal that is still, not really understood. So one of the things is, well, if you really have some early structures forming, maybe primordially induced, of course, maybe not primordial black holes directly, but some enhancement of small scale fluctuations, an early onset of structures in some way, well, that could be also leading to much higher radio background at early times. So maybe this is linked, and it's really interesting because this could be, of course, related to things that we have just recently also seen with JWST. We know that there is much more, activity in the early universe than we, would have expected from the standard lambda CDM model. I'm not saying that this is breaking lambda CDM, but there is something, an ingredient missing that we're not seeing at this point, right? So this could be all related already. And one direct link to the gravitational wave, signal that people have been discussing cosmic strings is actually providing a pretty good solution to this radio excess. We have with Bryce Sear and Sandeep Acharya, we calculated the signals from superconducting cosmic strings. I don't want to go into the details, but we ended up finding a solution to the radio excess. I'm not also trying to push that this is the solution, but I'm just saying there is a picture that emerges from early structures potentially forming. This could link to primordial physics. Maybe this is related to cosmic strings even. All this, together provides, I think, a lot of indications for, really thinking about these kind of things more seriously. And I'm really excited about, as I mentioned already, TMS and BZoo. Both of these will, in principle, allow to put constraints. So the blue line is our prediction for the cosmic string signal. Put constraints or limit some of these signals that could be produced in this way with measurements at 10 to 20 gigahertz and potentially then the higher frequency measurements. So this is an exciting direction. And again, spectral distortions. Because the physics of the high frequencies is linked to the low frequencies, this is really an interesting direction. And there's also the connection with 21 centimeter cosmology in an enhanced radio background. The 21 centimeter global signal, we heard about the edges, results and discussions related to that. And then, of course, fluctuations as well. If the dynamics of the problem at low frequencies is very different from what we think, that will be reflecting in 21 centimeter physics as well. This is something we have, recently worked on with relating to soft photon heating, which is, I think, a really exciting direction to think about. Okay, so now, as I promised, where's the link to the Hubble tension? So the link comes from the recombination lines. And I will try to explain this a little bit more. This is this wiggly signals here, which are coming from the high-level transitions of hydrogen and helium in the universe from the redshift 1000 universe, right? That's where the recombination radiation is coming. Then it's redshifting by a factor of 1000 and is now visible basically as this distortion in a wide range of frequencies. This is here a figure that is taken. I think this is from Yassine and my paper on the recombination calculations. These wiggles, they probe the dynamics and the real physics of the recombination process. So this is really interesting because if you, for example, change the recombination process, if something non-standard happens between the different phases of recombination, here's a figure that just illustrates where these lines come from. So the doubly ionized helium lines, they come from redshift 6,000, 18,000 years after the Big Bang. Then the helium-1 lines, the neutral helium lines, they come from redshift 2000-ish. And then the hydrogen lines, they come, in fact, if you would look at the lines, they come a little bit earlier. Maximum emission of the lines is a little bit earlier than even the last scattering peak, because at the last scattering surface, there's only about 16% of free electrons left. So they have recombined and emitted photons by trickling down in the states. They have recombined already much earlier. And the main emission is actually at redshift 1400, which is an interesting fact to just mention. But if something unexpected happens between these different recombination eras or during these recombination eras, this will reflect in the recombination lines. Okay, for example, here, this is an old paper, but I just wanted to show this figure that I produced there, where I just put some dark matter annihilation, and I basically show that the recombination spectrum, which here was calculated for only a 10 shell atom, that the lines actually change shape and the total emission changes shape. And this means that you can, of course, see, directly this different injection processes manifest. Annihilation is constrained very well with CMB anisotropies, but for example, if you have a dark matter decay or if you have some other excitation processes, you will see this reflected in the lines. And this is one way to just illustrate this. But the link to the Hubble tension comes from the fact that the recombination lines, they are also sensitive to the physics that is actually being discussed in connection with the Hubble tension. And I don't think I need to explain what the Hubble tension is about, but we have been talking about, for example, early dark energy, primordial magnetic fields, density fluctuations induced by primordial magnetic fields, to be more specific, varying electron mass. These are contenders that could be, explaining in terms of new physics what is going on with the Hubble tension. Basically reconciling the problem by fixing the, CMB anisotropic physics, right? And with Luke Hart, we have shown that the recombination lines actually change depending on what kind of physics you have. So, for example, here in the lower left figure, we're doing early dark energy models, and because early dark energy essentially leads to a different differential stretching between the different epochs of hydrogen and helium recombination, that leads to a change of the relative positions of all these spectra, and that changes the spectral distortions, of course. Similarly, if you have a varying electron mass or alpha, changes of the fine structure constant, that reflects in the shapes of the lines. And depending, of course, which models you're looking at, the responses are more dramatic or less dramatic. So this is, of course, not going to be an easy measurement because the recombination lines are the smallest distortion, but they are also having the most features. So in principle, you can experimentally hope to see them even through, heavy foreground obscuration. So this is just telling you that this is a way to probe the recombination physics. And if there's early universe physics involved in this, then this is a sensitive probe to this. And I just want to highlight again, before I go to the very last point of that, connection, recombination physics is really an important ingredient in our calculation of the power spectra. You put the theory of the NE, of the free electron fraction as a function of redshift into the Boltzmann codes. And we have been doing a lot of work to just calculate these kind of models properly, for example, with CosmoRec, but also HiRec, to really do the analysis back in the days of Planck data. And it is known that if we wouldn't put the right recombination model in, we would be shifting these contours. These are old contours. It's just an old figure illustrating the point. We were shifting them by several sigma, and we would be talking about different models than we are, in terms of like slow-roll inflation constraints. We would have had biased constraints. So this is actually a really important aspect of the calculation, and people forget about it, that you need to put in recombination physics to be talking about the constraints that we get in terms of cosmology. And we have highlighted this very recently with a paper that Gabriel Lynch and Lloyd Knox and I wrote, or two papers in fact, where we also responded to the DESI measurement of the dark energy, evolving dark energy, or indications for it. One should be more careful. But what we basically did is instead of putting in a recombination model, we actually reconstructed from the data the recombination model. Now we did this with a certain parameterization. That parameterization is not perfect, but because recombination is such a crucial ingredient, you can actually with the data reconstruct essentially the recombination history. And here's just on the in this figure you see a range of models that will be okay with the data. If you're like, oh, this wiggle here looks really wrong because this looks like it's not monotonic and so on. This wiggle, we have shown, Gabriel did a really nice demonstration where he basically smoothed out these wigglinesses and showed that it's the more global trend is actually important in terms of the real constraining power of the CMB anisotropies. So we have essentially not chosen the most optimal parameterization of this problem, but we can in principle learn about the recombination history. And one of the key conclusions is early recombination is what seems to be preferred by the data. And early recombination is also what helps fix the Hubble tension. So what I'm basically saying is recombination physics seems to be at least one contender for explaining the Hubble tension. And in reality, here's a comparison of the visibility functions for various models. Lambda CDM, so the standard model, and then the modified recombination reconstruction that we did, primordial magnetic field type history, and varying electron mass. Well, look at this. The varying electron mass, primordial magnetic fields, and the modified recombination, they all kind of lie on top of each other. So this just tells us that we are actually seeing a very similar manifestation, but just in a model-independent way here. If this is true, then the recombination lines should also be different. And that is a direct way to probe this. And if we want to learn about, things like varying dark energy and things like that, we cannot actually do this without assuming a recombination model. And if we marginalize over everything, we can actually, we obviously have different conclusions. And we, for example, show here in this second paper, we discussed that, when you do that things like the negative neutrino masses and stuff like that, they go away, right? So just as an indication for the recombination input is part of the analysis, and it's really important. And one really important demonstration that I thought was really nice to show, if we indeed have something like primordial magnetic fields inducing small-scale baryon perturbations at recombination, which is one of the ways of doing this, fixing the Hubble tension, then that would lead to small-scale fluctuations of the recombination lines as well. And if you average the recombination lines, it's not the same as taking the average parameters and then calculating the spectrum. So this is a demonstration that we did here with Matteo Luca and Aditya Roti, where we basically calculated, well, what is the averaging process? And we show that the recombination lines, are departing from the average when you're having this very, very large amplitude fluctuations in the baryon density. This is just a very simple, simplistic demonstration, but it makes the point that, again, the recombination lines, they could even give you a direct hint for the real origin of this. Is it something that's an average process, like varying electron mass, or is it something that is actually coming from a real granular universe at very small scales? And just to tie this all up again, well, who tells us that we're not seeing the onset of early structure formation, essentially? I'm not advocating primordial magnetic fields as the agent for doing this, but I'm saying we basically have indications with the Arcade excess, with the JWST, with potential recombination being fast, with the question for primordial black hole sourcing of supermassive black holes or the link of that, we have strong indications for the small scale universe just being very different from what we think. So again, I think that is my main point. All this might be all just one side. No, what is it? Two sides of the same coin. Well, it's multiple sides of one coin. So I think this is really exciting, and spectral distortions can help shed light on all this story. So this is really one of the reasons why I believe we should be super excited about this. If I have 5 minutes, Eleonora, is that okay? I will. I was initially thinking I will maybe talk about dark photon constraints and axion constraints that we can do with spectral distortions as one theoretical direction. In addition, enriching the monopole science, but I decided that it's actually more interesting to talk about spectral distortion anisotropies. But just very quickly, so. The monopole science is all, the spectral distortion science is normally always just the average sky flux, right? And I told you how I don't like the anisotropies. I'm just thinking about the average sky, the monopole. However, if you look at these processes here, then it is very easy to understand that most of them should lead to anisotropic injection of energy as well, right? So if there's something relating to dark matter, well, dark matter starts clumping, that would lead to some anisotropic heating. If it is clusters of galaxies, is an example that we are all understanding, gravitational collapse and the heating of the medium by the structure formation, well, this anisotropic distortions. So bottom line is anisotropic spectral distortions are absolutely expected. And if you have decaying particles or primordial black holes, dark photon conversion processes, all this will lead to anisotropic spectral distortions. Now, there's a problem, at least for the primordial universe, we cannot do that calculation, or until recently, we couldn't do this calculation because it basically means that you have to find another discretization instead of just having the K-space and the L modes discretized as a function of time. You also need now the frequency space as a function of time. And the thing that we realized is that there is actually a really efficient way of reparametrizing and discretizing the Green's function. So here is all the responses for spectral distortions for different energy injections. And instead of solving a system that had several thousand equations just to get this one monopole signal, we actually managed to compress this basically into a system that has like of order 20 equations. Which is a huge reduction of the dimensionality of the problem, and that allows us to basically discretize now in frequency and spatially and in L. So we can calculate with CosmoTherm. We can now calculate spectral distortion anisotropies and their cross correlation between the temperature modes and the mu distortion, the temperature modes and the Y distortion. And depending on, for example, here in decaying particle scenarios, what is the lifetime of the particle, you get this spectro-spatial information now that you can actually calculate and really get additional information about the universe and what is happening potentially at early times. And of course, the interesting thing is that this is targets for experiments like LightBird, for experiments. Even with Planck, you can put constraints on this, and we haven't fleshed out all those constraints. So this is something that we're now working on, and it is really interesting to think about this, because it's just the standard CMB anisotropy science that we can do, but now with spectral distortion as another parameter. So this is really exciting, and with David Zekiel and Tom Crawford and company, we have even shown that things like the SKA might be a really interesting way to put additional, to increase the leverage that we have on these spectral distortion anisotropies. We illustrated this with primordial universality, and what kind of constraints could you put at very small scales, so very high Ks, and how they are comparing to things that we can do at the CMB anisotropy scale. But the bottom line was, SKA with its different configurations can actually be an excellent low frequency foreground monitor, and even has direct constraining power on mu-type distortion anisotropies, which is a really exciting direction to do. And we are now working with the SKA. Within the SKA, we have initiated the discussion about really doing this in a more realistic way with instrumental settings and so on. But we did, I think, a reasonably good job in terms of not basing our analysis on actually real inputs from the blue books and things like that. So the spectral distortion anisotropy is something that we can also do, and we need to just basically harvest this information, put constraints on models. These are all new physics models, most of them, as far as I can tell, but it will rule out parameter space, and it's really exciting, I think, to think about this. And then, of course, look forward to real monopole measurements that we will hopefully have in a couple, at least in 5 years from now. I think that will be a major step, hopefully, forward. So that brings me to the end of my talk, where I hope that I convinced you that spectral distortions generally are just really exciting. Lots of really interesting physics you can probe. The link to primordial physics is, of course, the really exciting, fundamental physics probe. Of course, particle physics like dark matter physics, dark photons, axions, all this is also extremely exciting. But being able to basically probe the universe and cosmology and inflation physics in regimes that we haven't explored before, that I think is really exciting, and spectral distortions can do that. I briefly mentioned that with this arcade access, you might have a link even of spectral distortions and 21 centimeter cosmology. This is something that we worked in more detail out with Bryce Sear and Sandeep Acharya. So here's just a reference. I also generally, I didn't have time to talk about it, but spectral distortion measurements will provide a lot of information even for other communities like the line intensity mapping community. They will learn about the line monopoles in many hundred frequency bands. So this is extremely exciting in terms of opportunity for synergistic studies and combining different experiments. And then this is in a paper with that I just note there. And then the new opportunities with anisotropic spectral distortions. And I didn't put any conclusion here on the Hubble tension, but I think there's really good indications, strong indications that something is going on at small scales, and we need new ways of probing the small scale physics. We need new ways of constraining directly recombination physics. Rayleigh scattering comes to mind as another probe of the recombination physics. If there's something strange going on, then Rayleigh scattering physics will be modified. Of course, the CMB anisotropies directly are sensitive to the input recombination history, but we will still need to find different ways of shedding light on this kind of possibilities. And the recombination lines, of course, could be a really interesting opportunity there. And then, of course, the general formation process of primordial black holes or black hole formation, structure formation, early structure formation. All that is extremely exciting, and there's many, many things that spectral distortions can tell you, as I hope I convinced you. So I will stop there. Thank you.
Thank you so much, Jens. Great talk. Any questions?
Hi.
Luca, yes.
Great.
Hey.
So, hi, thanks, Jens. Thanks for this thorough discussion. It's really illuminating, and I have to rewatch everything because it's really a lot of meat. I just have one question in your first half of the presentation, so without discussing the remaining part. So, since we have a detection of the gravitational wave background at the nanohertz scale, so do you expect spectral distortion to give us information on the tilt if this background is of cosmic origin, which we don't know yet as of today.
Yes, absolutely. So there's the two ways that spectral distortions can potentially help with this. The direct tensorial constraints, I believe, will not be as easy to drive, because this figure, as which I showed, you see that measurements here and also smaller scale, they will drill down a lot, whereas spectral distortion limits on the direct gravitational wave backgrounds are just covering a window that other windows, other constraints will not reach. So I'm not sure that one can easily argue that way spectral distortions can help, but in the way in this way, if there is scalar-induced origin of this, something that leads to primordial black holes, for example, if there's some intermediate mass black holes involved in this that then ultimately lead, for example, to the supermassive black holes, if the stellar mass black holes are doing something, then spectral distortions, if you want to have primordial black hole formation, you need an enhanced power spectrum, but we know that CMB anisotropies put us at a very small level. At large scales, you have to get there somewhere, somehow, and you can't arbitrarily do this, at least within single slow roll inflation. So spectral distortions will ultimately be a really important test of a primordial origin of these kind of things. And if we believe that there's really some involvement of primordial black holes in this whole story, then I would say that spectral distortions have a powerful handle on the enhancements of small scale power, because even if you don't have obviously enhancement here in the direct spectral distortion regime, you will have to get there somehow, and Pixie is so sensitive, or versions of spectrometers that are being discussed, they are so sensitive that you would rule out a vast range of parameter space there. So I think the story linking this together, synergistic approach to this, will be really important. So yes, I would say that angle is extremely crucial.
Thanks a lot.
Thank you. Niels?
Hey Jens, thank you for the very nice talk. I just have a relatively simple question. You mentioned that BIZU is now in phase A. Do you know approximately what kind of constraining power for Y or mu we can expect from BIZU?
So BIZU, the hope is that we will detect the average Y distortion. The average Y distortion is 2 times 10 to minus 6, and we hope to detect it at 5 sigma. That's the target, and that seems to be feasible with the atmospheric noise that we will not be able to reduce ultimately, because that's the ultimate showstopper there. You can't arbitrarily drill down because the atmospheric noise is very uncontrolled. So that would be corresponding to an enhancement over FIRAS by a factor of 20 to 30 or so. With the mu distortions, the opportunity that we are now studying is combining it with TMS, because BIZU is limited to slightly high frequencies, higher than I would like, but there is of course budgetary constraints. You can't go arbitrarily low frequency, and the lowest frequency is somewhere in the 90 gigahertz regime, if I remember correctly, and that does not give you so much power, constraining power on the mu distortion, because the mu distortion is really discernible at low frequencies. So going down to 30 gigahertz or something is really helpful. One of the reasons why the SKA might be so powerful in really complementing anisotropy probes that we have, CMB anisotropy probes, is because it goes down to basically 5 gigahertz, which allows you to separate the different components better. So in terms of mu, we are still working on precisely saying what we can do, but it will be an improvement. I'm pretty sure in combination with existing other experiments over FIRAS. So I'm hoping that this will be also a step forward, a significant step forward. And in terms of timeline, if everything goes well, it depends a little bit, of course, on what CNES will do, because we're, phase A is now, there's still a decision to be made. Will it be flown or not? But if everything goes well, we could probably hope for a liftoff in 5 years from now, which is, I think, a really exciting timescale.
Perfect. Thank you so much.
Thank you. Sayantan?
Yeah. Thank you, sir, very much for this amazing talk. So I have mainly the first question I would like to ask is that you mostly focus on the temperature anisotropy or correlation, right? So I'm asking that as because you already talked about the pulsar timing array. What about the B mode? So you didn't talk much about the polarization I could see. So like already there has been a big blunder because of the bicep 2. So I am wondering that whether this could also give us pseudo B modes which are not actually the primordial origin or something. So could you just comment on that?
Yeah, so we have not included any spectral distortion, polarized spectral distortion treatments. That's pretty hard. I've been already talking to Cyril Petrou, or at least I've written to him because he's of course the expert on polarization transport. So I'm hoping that we can maybe do something there as well. But I just want to show this figure. Indeed, we looked at polarization correlations as well. So temperature E mode polarization and B mode we didn't consider in detail, but E mode polarization correlating with mu and with y from primordial physics. That's something we can do. I don't think that I don't see any simple way of really producing a spurious B mode signal from this physics, but I haven't thought about it, to be honest, in more detail.
Sure, sir. Thank you. And maybe one small question. And so I was asking that you mostly considered about the model like say varying electron mass or like alpha, etc., like various high energy like beta function changes type of model. And you probably pivoted it at the recombination at say 1000 redshift, etc., where we are getting. So I'm just wondering that I guess this anisotropy probably includes everything, but I was wondering that let's say from theoretical point of view, if I want to say the Zeldovich effect or the cross correlation between Zeldovich and Sackul's effect, that would also change like even the Sackul's effect. When you do the integrated Sackul's effect, there is alpha, etc., all the scattering cross sections, etc., there, right? So I am asking that are you actually only pivoting say fine structure constant at 1100 redshift and then forgetting that, or if you take the Sackul's effect integrated, you are continuing the alpha as a changing of say beta function of something like that? So that's what I was just wondering.
Yeah, so we have in the simplest models for for fixing the Hubble tension with electron mass varying, you usually think of it is constant at high redshifts, and there's no like real modeling of it going back to the standard value that we measure here. There is of course some work also by Niels and Leo Vacher that is considering some more models that are based on real scalar fields and where you have in principle time variations as well. Also with Dan Grin, we had a paper on alpha variations, but we haven't looked in detail at the effect of these variations on the CMB anisotropies, Sachs-Wolf, structure formation related terms. So obviously what goes as a propagation through the normal CMB anisotropies, that is included, but if you want to put some structure formation twist to this, there's probably more one has to do. We did consider with Luke Hart some very simple power law scalings as well. We found that power law scalings are not, there's no need to have any time variation really, because the main constraining power is really the redshift 1000 universe still. I would say that you run out of steam pretty quickly unless you cross correlate with low redshift props. Yeah.
So yeah, actually I was worried because in the Sackul's you get the integration over the exponential, right? I mean the integrated Sackul's. So even if it's a tiny over from say 7000, etc., it would mess up a big time. So that's what I was little worried. So thank you very much, sir. Yeah.
Thank you.
Thanks for having me.